All right. We're very happy to have José Cantarero telling us about configuration spaces of commuting elements. José, please.
Okay, thanks a lot, Sam, Jeremy, all the organizers. It's good to run into some old acquaintances haven't seen in a long time, and it's good to talk to a different public than the usual. So let me talk about this recent work with a master student of mine, Angel Jimenez, which I think is an interesting generalization of the spaces of commuting tuples, which are become very popular in the recent years. And it's not only a matter of generalizing because I want to generalize, but I think it could be useful also to understand these other spaces of commuting tuples, which have an interesting motivation. So let me start with that, with the motivation. And please, if you have any question, feel free to stop me anytime. So let me start with describing the space of commuting tuples in G. So you have a topological group, and you consider all the homomorphisms from C to the N to G. Now, this is equivalent to considering N tuples in G, which commute. So you have N elements, G1 to Gn, which commute with each other. And you can topologize this guy as a subspace of the product of G, N times. Now, this is not only a space, but it's also a G space. You have an action of G by conjugation. This is a continuous action. And the quotient is also an important space for homology, which is a space of representations of C to the N in G. So, it's a space of commuting tuples up to conjugation. Now, why did people study these spaces? Well, the space of representation parameterizes flat connections on principal G bundles over the n-dimensional torus. More generally, the space of representations of the fundamental group of a space parameterizes flat connections over the space. In this case, the fundamental group of the torus is C to the N. Now, this is the sort of the motivation for differential geometry in some sense, or topology, but the motivation came strongly from theoretical physics, because in that case, you can interpret these flat connections over principal bundle, etc., as a classical modular space of zero energy states on T to the N, whatever that means. I mean, don't really ask me about the theoretical physics because I don't know much. I only translate what I can. So the reason why this space was important is because it worked as a kind of an input for some work of Witten, which was trying to compute the supersymmetric index, some kind of index of a differential operator. And to compute this index, you needed to consider this space of representation. And when he did this computation, he got the first time R plus 1, where R is the rank of the connected compact Lie group that he was considering. But in physics, this number was expected to be the dual Coxeter number of the group. Another number that you can associate to the compact Lie group, which does not necessarily coincide with R plus 1, but in some cases it does. Then this discrepancy was found by Witten to come because he had done something wrong, and he had assumed that the space of representations of C3 on G is path connected, and in general it is not. For example, for spin 7, it is not path connected, and there are many other examples where it is not. So this is the motivation. Oh, sorry. And from that point, many people started studying these spaces from the point of view of algebraic topology. I mean, there were some people who studied these spaces before, like Goldman, but he had another point of view, like studying from the point of view of symplectic geometry, more geometrically. Now, topologically, of course, the first thing you should study, considering the motivation, is if this space was path connected or not. And they studied this for the space of homomorphisms, and Adam and Fred Cohen did this. So this is path connected when every abelian subgroup of G is contained in a connected abelian subgroup. This happens, for example, for the special unitary groups, for the unitary groups, for the symplectic groups. For cohomology, Tom Baer found this very nice formula to compute the cohomology of a certain path component of this space of homomorphisms, the path component which contains the element 1, 1, 1, 1, 1. And it's very nice because you can compute it as invariance in terms of the Weyl group. Okay, as long as the characteristic of the fit does not divide the order of the Weyl group. And well, I wanted to point out this example because I'm going to be using it later. And there were many other homotopy invariants that were studied for these spaces. For example, the suspension of this space, the space of homomorphisms into SU2 was determined. The fundamental group, the equivariant K-theory, rationalized. There is also an interesting phenomena that these spaces, when you move in N and in M, you can assemble them and form an infinite loop space, which gives you another cohomology theory, which is called commutative K-theory. There are also generalizations of this, which are called nilpotent K-theory. Two other works that are very related to what I'm going to talk about today is the works of Dan Randras and Staffa, which dealt with homological stability and representation stability. So in a sort of relatively recent paper, they showed that with respect to the number of elements in the tuple, these spaces satisfy uniform representation stability. And when you take one of the classical sequences of compact Lie groups, they satisfy a strong rational homological stability. Okay. And I'm mentioning here also Kishimoto and Takeda, because after Dan Randras and Staffa, they proved this homological stability. They improved the bound. And well, I have to say that I'm not being exhaustive with respect to all the results that have been done on these spaces, but I don't want to take forever. So I'm sorry for all the results that I didn't mention, if there's anybody in the audience. Now, so let me now go to the spaces that are, staring in this talk. So in this case, we're going to generalize the space of commuting tuples with the space of configurations of commuting elements. So now, not only do I impose that the elements have to commute, but the elements have to be different. Okay. Now, what was the initial motivation for me and for my student? Well, when I proposed this problem to him of studying these spaces, my idea is that these spaces will be less singular. They will have less singularities. It will be easier to study them. And in the sense that, they are an important part of this space. And in the future, you could think that you could get from this space to the space of homomorphisms by filtering. So this is kind of like the first step in a possible filtration. Now, of course, other motivations is that configuration spaces, appear a lot in algebraic topology and different versions, like label, like equivariant. So why not? And another motivation, which is really a bit loose, is that you can also think of commuting operators when you think of a unitary group of an infinite dimensional Hilbert space as observables in quantum mechanics. So this corresponds to studying a parametrization of the different observables that are compatible. These observables that are compatible is that observables that when you measure one of them, it doesn't affect the other one. That, when you don't have this sort of Heisenberg phenomenon. And of course, another motivation, but actually this came later, is that you have cohomological stability phenomena for the space of homomorphisms and for the space of configurations. So it was natural to ask the question whether you will have also stability phenomena for these spaces. And in fact, this was a question that was raised by Ramras Stafford in the paper that I mentioned before. Okay. So let me start with a very simple example. The space of configurations of two elements in SU2 which commute. In this case, you can determine the homotopy type completely. It happens to be homotopy equivalent to SU2. And it's very simple. You have a map from SU2 to this space, which takes a matrix to that matrix and minus that one. And the other map is just the projection to the first coordinate. One composition is clearly the identity, and the other one is homotopic to the identity using this homotopy that you usually see in your first course in algebraic topology. Now, the only thing that you really have to check for this homotopy to work is that this is well defined, and that this space is and that this matrix is different from that one and commutes with this one. But this is actually simple too, because if you have two commuting matrices in SU2, you can also think of them as commuting unit quaternions. And if two unit quaternions commute, their imaginary parts have to be parallel, which means that they have to be both multiples of the same guy. I mean, the real part can be anything, but they have to be multiple. And then when you do this computation, well, of course, it's going to be also parallel to that one, because you are only multiplying by t and 1 minus t and dividing by a number. Okay, so this is simple. Now, the main tool that is used in this paper is this theorem by Baer, which is in this work that I mentioned before, which is kind of general. If you have an action of a compact connected Lie group on a compact Hausdorff space, and the isotropic group of any point is what is called a maximal rank subgroup, that is contains a maximal torus, then when you restrict the action to the fixed points, then you get a map from G times xt to x. This is not a principal bundle, but Tom Baer in this article, and I believe that in his PhD thesis, develops what is called cohomological principal bundles. So what is a cohomological principal bundle? So the idea is here in this diagram below. The idea is that you have a free action of the normalizer, and this is the quotient by that free action. This is not a principal bundle, but this map, the action map, factors through the quotient. The action has to be a closed surjection, and also this H, the fibers are F acyclic. That is the cohomology of the fibers, not the homotopy fibers, the real fibers. They have the same cohomology as the point. But this works when the characteristic of the field does not divide the order of the Weyl group. And a nice thing about these cohomological principal bundles is that they can be used to compute cohomology. So you get a formula that computes the cohomology of X in terms of the cohomology of this product and taking the fixed points. Okay, and since we are over a field, this cohomology It's also relatively easy to compute. Well, I mean, of course, it depends on X, but the cohomology of G over T over as a module over the Weyl group is well known, is the regular representation. And you're gonna get the tensor product of them, and then you only have to find the fixed points. So this is a nice formula. Okay. So now I want to apply this to the case of SU2. In the case of SU2, but now when K is greater or equal than 3, you also have a closed surjection. Yeah, because the result of Baire applies in this case. But not only is it a surjection, but it's also injective. Because if two elements go to the same element here, it means that you have two sets of elements that when you conjugate it, they are the same, right? That they are conjugate in SU2. But SU2 is a group that is very small. And in this case, if you have two sets of elements which are not in the center, and they are conjugate in SU2, they are also conjugate by the normalizer of the torus. And because we are imposing that K is greater than 3, greater or equal than 3, and the center of SU2 only has two elements, at least one of the elements has to be non-central. And therefore, they have to be conjugate by the normalizer, which means that they are related by the action of C2. This C2 is a Weyl group of SU2. Okay? Therefore, this map is a homeomorphism. And the space of configurations of the circle is well known. You can break it as the product of the circle and the configurations of K-1 points of the interval 0, 1. This space is homotopically discrete, and it has one component for each element of the symmetric group on K-1 letters. And this action of C2, what it does is that on this space, which is the two-dimensional sphere, is the antipodal map. And on this space, what you are doing is on S1, you have the complex conjugation. And of sigma K-1, you have an action that permutes points. Therefore, this action is permuting all the different summands that you have in here. So at the end, you get just a disjoint union of products of S2 with S1. So I mean, this is nice. You have determined completely the homotopy type. And you know, I wanted to point out this example because when I mentioned the motivation, I said that my idea is that these spaces are less singular than the space of commuting tuples. And this is something that you can observe in this case. If you look at the space of commuting tuples in SU2, the homotopy type of the suspension was determined by Baire, Jeffrey, and Selig. But look, for example, in the case of two tuples. This is the homotopy type of the suspension. It's quite complicated. Or for the case of C3, it's even more complicated, and it doesn't get better than that. I mean, as you increase the C to the N, the formulas are similar. They have very explicit formulas in that paper. And before suspending, you have a homotopy push out that determines the homotopy type of this space. But again, it's not that easy compared to the results that I gave you earlier for the configuration space. Okay, everything good so far? Any questions? Okay. Okay, so from now on, I'm going to assume that the compactly group that I'm going to be dealing with is a product of groups which are special unitary groups and symplectic groups. And I forgot to put here a finite product. because I still want it to be compact, so a compact Lie group. And the reason why I'm imposing these conditions is because I want the fixed points under the conjugation actions of the torus to be the configuration space of the torus. Now, why is that? Let me go back a couple of slides. I want that because I want to use the theorem by Baird. And in this theorem, you have the fixed points under the action of X. So I want that these fixed points will be the configuration space of the torus. Of course, you could do this in more generality, but you will have to consider these fixed points instead of the configuration space. Now, using Baird's theorem, I can compute the rational cohomology.
May I ask a question, Jose?
Sure.
How is compactness relevant for this statement?
Well, because otherwise you wouldn't have generally a maximal torus, right?
I mean, any Lie group has a maximal torus, no?
When any connected, yes.
Yes, any connected, yes.
Right.
I thought your worry
the
was that it
Weyl
would
group?
be infinite dimensional, in which case it wouldn't be a Lie group.
Right.
So compactness is not an issue here? I mean,
Uh,
non-compactness is not an issue.
I mean, if it's not compact, let me see. Well, you also need that the Weyl group will be finite. Right. In that case, you wouldn't have a finite Weyl group, right?
And for example, for GLNC,
Mhm.
it's not compact, and the Weyl group is finite, right?
Right. Okay, you mean yeah? Could I include here GLNC? Yeah, I could include that too. Yeah. I thought that you were, yeah. I was thinking about the finite product, but yeah, you can also include here groups of the form GLNC, and that will work too.
Okay.
For some reason, we didn't include those, but yeah, you're right. Yeah, you're right. I mean, what we want really is that these groups, SUN, UN, SPN, and also GLNC, what we wanted to hold is that when you look at abelian subgroups, they are always contained in a connected subgroup. And these are conditions that not every Lie group satisfies, but these groups and GLNC, like you mentioned, they also satisfy. And that's what we need for this equality.
Okay.
Okay, thanks.
Jose, maybe you want them all to be conjugate to a maximal torus with a compact assumption.
Do I want who to be conjugate?
The other. So sorry, maybe I'm confused. But do you want maximal torus so that all other torus are conjugate?
No, not really. I mean, what I need is that every abelian subgroup can be fit inside a maximal torus.
Oh, okay.
Yeah. Okay. So under this condition, then I can apply Baird's theorem, and then I can compute the cohomology as a fixed point. And in fact, this computation computes the cohomology ring, even the cohomology ring. And Randrath and Stafford, they also showed that this argument can be modified a bit to show that for homology, you also have the this isomorphism. So I'm going to use both cohomology and homology. So let me go to the homological stability result, which are maybe some of the results that people are interested here. I have to say that Jeremy really contacted me real quick after I posted this preprint to the archive. He's really on the lookout. But that was nice. But I have to say also that the homological stability and cohomological stability results are really very elementary in the sense that they follow quite easily from other homological stability results that we had previously. So anyway, what I'm going to consider now is one of these families of classical groups. And because I'm only considering this SUN, UN, and SPN, these are what the groups GRs are going to be. I think I'm missing something here. Anyway, this GR is going to be the unitary group UR, SUR+1, or SPR. The notation only indicates the rank of the group. Okay, so these are all groups of rank R. And these classical families, they fit each of the groups inside the next. When you think of them as matrices, like putting an extra one in the matrix at the end, and you're like putting in a diagonal block. And that gives you a map from the configurations of GR to the configurations of GR+1. Okay, just regarding an element of GR as an element of GR+1, putting that extra one is not going to affect the commutativity or the fact that they were different. And when you look at the action map, since you can also think of these configurations as tuples, as commuting tuples, you have two actions. You have the conjugation action of GR over the configurations of the torus, or you have the conjugation action of GR over the torus, over k copies of the torus. This action factors through the quotient with the torus because the torus is abelian. And because the action is just conjugation, this diagram is commuted. So in fact, this isomorphism that I mentioned earlier, that you have for this space and you have for this space too, since that isomorphism is induced by this map, you're going to have also a commutative diagram with homology. Okay? And again, this map going down, it's easy to see that is W equivariant, where W is the Weyl group. So it also goes to the fixed points. And now the point here is that the inclusion of the configuration space in the torus is R-1 connected. We know the connectivity of this map. This is very classical, and that is known for manifolds. So here we are using this is a finite dimensional manifold. I think somebody mentioned that before, and here I need that because that has to be with the dimension of the manifold. And now, because this map is R-1 connected, it induces an isomorphism in homology in dimensions below R-2. We have these two isomorphisms by Baird result. So we're going to have the same isomorphism here in the same range. So if we have rational homological stability for these spaces, we will have the same kind of homological stability for these spaces. Okay, it's that simple. And homological stability for these spaces is known by the work of Randras and Stafford. So we have the same, so we have the same bounds as long as you have the R is greater or equal than m-2. So we have to impose two bounds. The R is greater than that, and the bound that Randras, Stafford, or Kishimoto and Takeda found. Anyway, I'm not going to repeat the formulas. It's not that important, these numbers now, but this is the idea. Now, I wanted to talk also about stability with respect to the number of tuples. And here there is an important difference with respect to the space of commuting tuples, especially an important difference if you consider the work of Randras Stafford, because what they do is that, if you have a commuting tuple, you have a tuple with k commuting elements, you can create a tuple with k plus 1 commuting elements by adding a 1, just the unit element of the group. But here we cannot do that because it may happen that in the tuple that we started with, we have the 1 already. So we cannot repeat the element 1. So we don't have a canonical map going up. But we can think of these spaces. Oh, sorry. I'm missing here the AB. This should be a space of configurations, spaces that commute. So sorry for the typo here. But we can think of them as configuration spaces. And here we were inspired by the work of Tom Church. So remember that one way of thinking about representation stability is thinking as of Fi modules. So Fi, recall, is the category whose objects are these finite sets, and the morphisms are given by injective maps. Now, when you have an injective map between two of these sets, that induces a map between these configuration spaces of commuting elements, which is given by choosing the images of the n elements, of the elements of the set n. Now, this gives you the structure of an Fi space or a co-Fi space. But when you take cohomology, now you will get a sequence of Fi modules. And in terms of a sequence of sigma R representations, these maps are the ones induced by forgetting the last coordinate. Okay, so you go from configurations of 2 elements to configurations of 1 element by forgetting the last coordinate, and from configurations of 3 elements to 2, forgetting the last coordinate, so on. You have a sequence here where you have the action of the symmetric group by permuting the elements of the tuple. And this is what is called a consistent sequence of sigma R representations over the fields of the rational. And now, for this sequence to satisfy uniform representation stability, what we would like to see is that these Fi modules are finally generated. And in this case, that happens by using again this description of the cohomology as fixed points. We also have that these maps that forget some of the elements commute if we put here on the right side the map induced by the identity on the first factor and the map that forgets the same elements. I mean, the map that will do the same formula that I did on the right side, but on the configuration space of the torus. But the right side now, by Kuneth, is this tensor product. And now this part is a constant Fi module, so it's finally generated. And this also is finally generated as an Fi module by the work of Tom Church. And when you have 2 Fi modules and you tensor them, or you take a direct finite sum of them, that again happens to be an Fi module. And when you take the fixed points by an action of a finite group, this again is a Fi module by work of Randras and stuff. Okay, so therefore, these spaces are going to be, this sequence is going to give me a finally generated Fi module. Therefore, I'm going to have a uniform representation stability over the rationals. And something that I haven't mentioned, but it works for these 2 examples, is that you don't necessarily need to have the rational number of coefficients. You can also use a field whose characteristic does not divide the order of the Weyl group. I only chose to write rational here, for simplicity for the talk. But if you look at the paper, you will see that you can use any field with that, with those conditions. I think somebody wanted to ask something. Maybe? maybe not. Well, okay. And then once you have uniform representation stability, you have a nice consequence for the quotients by the action of the symmetric group. So this space is also, you can think that is also new, will be the space of unordered configurations of commuting elements in G. And so you will have that destabilized too when G is a connected compact Lie group. But here they stabilize only as rational spaces, as rational vector spaces, because you don't really have maps between them that induce this isomorphism, but you have this sort of rational stability, not strong.
Have you seen this, I guess, old work of like a Rohit Nagpal on periodicity with mod P coefficients for configuration spaces?
No, I don't think I have.
Oh, okay. Maybe after the talk, I'll like send it to you, or I'll put it in chat now or something. But you might expect that if you took finite field coefficients, but you know, whatever, not dividing the order of the Weyl group, that the homology wouldn't stabilize in the unordered case, but that it would be periodic with period P. But we can talk about this after the talk.
Okay, sure. Yeah, thanks. But I'm confused. You say that you should not expect if the coefficients are, if the characteristic of the field does not divide the order of the Weyl group, you should not expect to have stability. Is that what you said?
Oh yeah. I'm saying that, yeah, with mod P coefficients, I still wouldn't expect stability, but that maybe like if you look at the like homology of points in S2, that is like Z mod 2 minus 2 times the number of points. So like if you take it with F3 coefficients, then it's like 0, 0, F3, 0, 0, F3, 0, 0, F3. So, you know, it with F3 coefficients, it doesn't stabilize, but, you know, like if you change the number of points by 1, you might be comparing 0 and F3, which are different. But if you increase the number of points by 3 at a time with F3 coefficients, then it does stabilize. And so you might expect, you know, if you look with FP coefficients and it doesn't divide the order of the Weyl group, that you would have this periodicity instead of stability in the unordered case. I think it's not automatic, but that's what I would expect.
Well, yeah, maybe we can talk after the talk, because I actually lost my connection there for a moment, so I couldn't hear the whole thing. Can you hear me now? Well,
yeah, maybe I think you need to reshare screen, and maybe we need to pin you or something. I don't know.
Oh.
Yes, I'm going to do that again. Could you share your screen, Jose? You're muted.
Let me share my screen again.
Yes, please.
A good thing that we are used to these problems now. I can't seem to be able to share my screen now.
Well, everyone is allowed to share a screen.
You might as well make him a co-host.
Yeah, let me try.
That should fix the problem, even if There should be another fix.
Okay. How about
Okay, now I can. Yeah. It was a problem that with Zoom. Yeah.
All right, very good.
Okay. Oh. Okay, sorry about that. Okay, so let me go back to where I was. Right. So we have the stability of these rational cohomology groups, and this is kind of interesting too, as I was mentioning, because you don't have natural maps between them, right? You don't have this, even the maps that you had for the unordered case, which forgot some of the coordinates, you don't have them anymore here in the unordered case. Well, as it happens to for configuration spaces. Okay, so this is actually all that we have about homological stability. But of course, when you have homological stability or representation stability, what one should do is really try to reach the stable range. That will give you a really strong result, because you will have the whole of your cohomology computed, at least in theory. We have some other computations then in the unstable range, although we didn't reach the stable range, even though that was the intention. So one thing that we can do is to compute the cohomology in dimension 1. Okay, so I mentioned earlier that the inclusion of the configuration space in the torus, in the product of k copies of the torus, it was R minus 1 connected. Okay, where R was the dimension of the torus. So when the dimension of the torus is at least 3, you will have that this is 2 connected, and you will have an isomorphism of H1. But when the dimension is 2, even though you will have only that this map is 1 connected, but you can also study what happens in the fundamental group and see that the commutator subgroup is contained in the kernel. So in this case, you also get an isomorphism in the first homology group. And therefore, you can sort of do the same thing that we did before, comparing these two spaces to relate the cohomology of this space with the cohomology of the space of commuting tuples. And the cohomology of commuting tuples in dimension 1 is well known, at least in these cases when G is a product of these sort of groups, SUN, UN, SPN, because in this case, this space of homomorphisms is path connected. Okay, so then the component that contains the element 1, 1, 1, 1, 1 is the whole space, and the result of Gomez, Petit, and Soto show that the fundamental group is just the fundamental group of G to the K. So then, you know, the homology or the cohomology with rational coefficients can be determined for this. We only need that the rank of the group is at least 2. And of course, this is something that I've been using all the time, is that G is in the family of finite products of these sort of groups. Now, some of the computations that we did that were sort of, you know, let's see how much we can compute, is the case of the configurations of 2 elements for a group of rank 2. Okay, so we looked at all the cases of these groups of rank 2. In this case, you have the configurations of 2 elements in the torus, but because T is a group, is a topological group, this configuration space is homeomorphic to T times T minus 1. And using this, we can determine the structure of these cohomology groups as modules over the Weyl group. This is well known to be the regular representation, but again, you need to determine in each dimension which representation of W it is. And once you have it, You can tensor them, use one of these tables for the tensor products of or representations of finite groups, or simply just multiply their characters. You can determine this as a representation of W, and the fixed points are going to be the multiplicity of the trivial representation. So once you have these multiplicities, you get the cohomology of this space over the rational number. But actually, you can do a bit more. If you push the computation a bit further, you can get all the multiplicative generators and all the additive generators of this cohomology, because for representations, if you follow all the steps, you can get which elements of these representations generate the trivial representation. And that way you can find all the multiplicative and additive generators. It's a bit of a mess because you have a lot of generators and you have to find how they multiply. Many of the products are zero, fortunately. And you can find the rational cohomology ring. Although we didn't do this for all the groups because, as I say, it's a bit of a mess and we only did the ones that were cleaner. And in these cases, you can also find the cohomology of the space of unordered configurations. Okay? Because this space, this cohomology is going to be the fixed points under the action of C2, but now C2 acting by permuting coordinates and finding the fixed points. And this was a fun thing to do. Let me show you some of the computations that we did. For example, the cohomology of this space happens to be generated multiplicatively by these 5 elements and these certain relations. So we really don't understand which space this is. It's still a bit complicated. But in the case of unordered configurations, we actually kind of got a bit of a surprise because their cohomology rings happen to be simple. They are just exterior algebras. Now we haven't figured out the homotopy type of these spaces. And of course, we have the same result with over fields which do not divide the order of the Weyl group, which in this case will be over fields whose characteristic is different from 2. So you will also have these exterior algebras in those cases, but we haven't found any obvious relations, for example, between this space and U2 or the product of S1 and S2, SU2. I think it's something interesting that we are interested in continuing to look at these homotopic types. And we also have the computation of the cohomology of the configuration space of 2 elements of S1 for SU times SU2. I haven't written in here, but it's a similar result to this one. It's something that is also maybe a bit more complicated here that in the space of commuting tuples is that for commuting tuples, the space of commuting tuples of G times H is the space of commuting tuples of G times the space of commuting tuples for H. And we don't have here that anymore. Okay, so that's why, computing this is not just computing for S1 and computing for SU2. You have to do it anyway. A bit more challenging computation was trying to do the configuration space of 2 elements, for 3 elements for U2. In this case, the configuration space of the torus, you can also take out T, again, for the same reason, because it's a topological group, but you are stuck with this configuration space of 2 elements in T minus 1. You cannot reduce that anymore, at least not that simply. But this space is still quite well known. I mean, you can find stuff on them. And in particular, you can find things like the fundamental group. But the process is kind of the same as before. We already know what the cohomology of this space is as a module over the Weyl group, which in this case is C2. Now we need to know the cohomology of this space as a module over the Weyl group. And to do that, what we do is use this vibration by Fadel and Nowirth, which is given by projecting to the last coordinate. So you will project to t-1. T-1 will be a classified space for the free group on 2 letters. And the homotopy fiber, well, in fact, this is a vibration, so the fiber will be t-1 and another point in the, well, and the point that you chose as the base point. And this is a classified space for the free group on 3 letters. Now, as I mentioned, the fundamental group of this space in the middle is well known, and you can use the Z spectral sequence to compute the remaining cohomology group, which will be H2. Yeah, above H2, everything will be 0, and you have to compute this cohomology with local coefficients. But also, because of the nice presentation that you have on the fundamental group, it's easy to find the action of F2 on F3 that is given by this by the short exact sequence of the fundamental group. And using the same result as using the same process as before, we got to this computation of the rational cohomology of this space. But unfortunately, this still doesn't reach the stable range. And we'll have to get up to 4 to reach it. Okay, so, well, this is really all I had to talk about the paper. Let me tell you some things that we are interested to know more about these spaces. We would like to know about the fundamental group, because we don't have, in general, the formula by Gomez, Petit, and Soto doesn't hold. I mean, we know that in some examples you don't have it. Even though the cohomology, the first cohomology or the first homology happens to be the Abelianization of what you expect to be the fundamental group. So maybe in those cases you will have that the fundamental group agrees to. We haven't done that yet. Of course, we would like to have more cohomology computations to see a more clear pattern. I mean, we've seen some nice computations, and in some cases we got these exterior algebras. So of course, in those cases, we would like to determine the homotopy type of these 2 cases that are at the end. But we need more computations to get a more clear view of the pattern. And of course, the bounds that we have for stability. To be fair, we haven't done anything about it. We only use the bounds that Ranra, Staffa, Kishimoto, and Takeda had. So it would be nice to see if those bounds are optimal or if they are different from the case of commuting tables. Okay. So yeah, I think that's all I have to say. So thank you for listening.
Thank you very much. So, thank you. Jose, is there any question? So maybe I ask a question. Again, going back to the compactness issue, I remember I was told that is that correct that the space of commuting elements in a Lie group is homotopy equivalent to the space of commuting elements in the maximal compact subgroup?
Yeah, that's right.
Is that correct for any Lie group?
Yeah.
Okay.
Really. Yeah.
And I think you need reductive, no? Is that not an Lie group?
Oh, hi, Bernardo.
Okay, Sam.
Good to hear
Okay.
you.
Okay, yeah, we have an expert on that here in the audience. Yeah, I think I believe Bernardo's probably knows more about this than me. Yeah, we haven't really thought of much about groups that are not compact, but yeah.
So I was about to ask, is the same true for configuration, abelian configuration spaces of non-compact Lie groups?
We don't know. We don't know. But we'll think about it. Yeah.
Very good.
Yeah. I mean, this is the first. This is kind of the start of the project of studying these spaces. And to be fair, this is all we have so far. We have many questions related to like similar results for spaces of commuting tuples. So there is a lot to think about. I hope that we could continue figuring out those questions.
Very good. Any other question?
Maybe I can ask something. So I was a bit late to the talk, so I missed a little bit about this conjugation map. Well, which I'm guessing you're using.
Yeah.
So in commuting elements, you usually go from the conjugates, well, the space of conjugates of the torus to the K to the one component, to the connected of the identity representation of the home space. So in this case, what happens? I mean, you don't have like this distinctive.
Yeah, we don't have that distinctive component, right? So, I mean, that's why from the beginning, I put that condition that G is a product of groups of this form, so that the fixed points will be the configurations of the torus. And in those cases, the space of configurations of commuting elements is always path connected to. So you don't have to worry about the connected component.
Oh, I see. So you can't, right. So you can't have a similar statement, like if you want to allow any compact, say any compact connected Lie group, or even say simple compact Lie groups.
Right. Yeah, I mean, we wouldn't have we will have a similar statement if we change this by the fixed points of the configurations by the action of the torus, but this space of these fixed points will probably be disconnected, and then we don't have, like you say, we don't have a distinctive component. I mean, we thought about that in some cases you do have a distinctive component, but they're only when K is small. When K is small, you can use the component of the tuple that contains central elements. Okay, but as you move, when K gets bigger, then you don't have enough central elements, so you don't have so you don't have a tuple to choose as your base point.
I see. Yep. Okay, thanks.
Yeah, thanks, Bernard.
All right. Well, if there is no other question for Jose, we thank him again.
Thank you.
I hope the bank issue will be resolved soon.
I hope so, and I have to come back now.